Hello dear students, all of you welcome to Vidyan classes. It is the 10th lecture on function and the second lecture on binary operation. Today we will discuss some important type of binary operations. First, commutative binary operation. What is commutative binary operation? Definition: a binary operation star on set A is said to be commutative. A binary operation star on set A is said to be commutative if A star B is equal to B star A for all A and B belongs to A. What is commutative binary operation? A binary operation star on set A is said to be commutative if A star B is equal to B star A. Binary operation is a function from A cross A to A. It is the definition of a commutative binary operation. Example: so that addition and multiplication are so that addition and multiplication are commutative binary operations in R. R means set of real numbers. So that addition and multiplication are commutative binary operations in real set R. A binary operation star on set A is said to be commutative if A star B is equal to B star A. If this condition is satisfied for all A, B belongs to A and B belongs to A. So that addition and multiplication are commutative binary operations in set of real numbers. Solution: case 1, that is addition. Addition, that is denoted by the plus sign, so that R cross R to R. R is the set of real numbers. AB order pair belongs to R cross R addition, that is plus sign, operates on AB order pair gives A plus B belongs to R. For all A and B belongs to R. Implies this addition denoted by plus sign is a binary operation in R, set of real number. Clear? Addition is a binary operation in R. Since the plus sign operates on AB order pair gives A plus B in R. Is it true? It is always true. Plus sign operates on, that is addition operates on AB order pair gives A plus B in R. For all A and B belongs to R. Therefore, addition is a binary operation in R. Again, since A plus B is equal to B plus A, for all A and B belongs to R. Since A plus B and B plus A are same, implies this addition, that is plus sign, is commutative in R. Since A plus B is equal to B plus A, for all AB belongs to R. Addition of two real numbers is a real number. A plus B is the same as B plus A in R set. That is, addition is a commutative in R. Here, addition is a binary operation in R. Here, addition is commutative in R. Therefore, addition, that is denoted by the plus sign, is a commutative binary operation in R, that is set of real numbers. In first part, we show that addition is a binary operation in R. In second part, we show that addition is commutative. Addition is commutative in R. In general, we can say addition is a commutative binary operation in R. Clear? Addition is a commutative binary operation in set of real numbers. Case 2. Case 2, we have to show multiplication is a commutative binary operation. Solution: multiplication, which is denoted by the into sign, R cross R to R. AB order pair belongs to R cross R. A into B belongs to R is 2. for all AB belongs to R. Product of two real numbers is a real number. So A into B belongs to R. Multiplication, that is into sign, operates on AB order pair, gives A into B in R. It satisfies the definition of a binary operation. Implies this. The multiplication is a binary operation in R. Since multiplication operates on AB order pair, gives A into B in R. It satisfies the definition of a binary operation. In second part, since A into B is equal to B into A for all A and B belongs to R, that is set of real numbers, implies this. Multiplication is commutative in R. Multiplication is a binary operation in R and multiplication is commutative in R, since A into B is equal to B into A. Product of two real numbers is a real number. Therefore, multiplication is a commutative binary operation in set of real numbers. Clear? Multiplication is a binary operation in R, and multiplication is a commutative in R. Multiplication is a commutative in R. Multiplication is a commutative in R, and multiplication is a binary operation in R. Therefore, multiplication is a commutative binary operation in set of real numbers. Are you clear? Okay, note down. Next question. So that subtraction is not a commutative binary operation in set of real numbers. In second bit, division is not a commutative binary operation in set of positive real numbers. Solution, first bit. Subtraction is not a commutative binary operation in set of real numbers. Minus sign, so that it is the symbol of subtraction. R cross R to R. R is the set of real numbers. AB order pair belongs to R cross R. Minus sign operates on AB order pair, gives A minus B in R is true for all AB belongs to set of real numbers. Since subtraction of two real number is a real number, implies subtraction is a binary operation in set of real numbers. Since a minus b is not equal to b minus a, implies subtraction, that is minus I, is not commutative in R, that is set of real numbers. Subtraction is a binary operation in R, but subtraction is not commutative in R. Therefore, subtraction we have to show subtraction is not commutative binary operation. Therefore, subtraction is not commutative binary operation. Therefore, subtraction is not commutative binary operation in set of a real number. Subtraction is a binary operation in R, but subtraction is not commutative in R. Therefore, subtraction is not commutative binary operation in R. Clear? Second bit. Solution to second bit. Here we can give an example. 3 minus 4 is not equal to 4 minus 3. Division is not a commutative binary operation. Division so that set of positive real number cross set of a positive real number. R plus cross R plus 2 R plus, that is set of a positive real number. AB order pair belongs to R plus cross R plus. Division operates on AB order pair gives A division B. Is true. Implies for all AB belongs to R plus, that is set of positive real numbers. Division of two real numbers is a real number when both are positive. Implies division is a binary operation in set of positive real number. Since A division B is not equal to B division A for all AB belongs to R, plus, that is set of positive real numbers. For example, 3 division 4 is not equal to 4 division 3. 3 division 4 is not equal to 4 division 3. In general, A division B is not equal to B division A for all AB belongs to R plus. That is set up for real numbers, which implies division is not in division is not commutative in set of positive real numbers. Division is a binary operation in R plus, but division is not commutative in R plus. Therefore, division is not commutative in binary operation, is not a commutative binary operation in R plus. Clear? Therefore, division is not a commutative binary operation in set of positive real numbers. Clear? Okay, note down. Note down. Next, associative binary operation. Definition of associative binary operation. What is the definition of associative binary operation? A binary operation star on a set capital A is said to be associative a binary operation star on a set, that is non-empty set, is said to be associative if A star B bracket star C is equal to A star bracket B star C for all ABC belongs to capital A. It is the definition of associative binary operation. A binary operation star on a set capital A is said to be associative if A star B bracket star C is equal to A star bracket B star C for all ABC belongs to A. Star is the binary operation on A. Question: so that addition and multiplication, so that addition and multiplication are associative binary operations in set of real numbers. So that addition and multiplication are associative binary operations in the set of real numbers. Solution: case 1, that is addition, plus sign represent the addition so that R cross R to R. AB order pair belongs to R cross R. The addition operates on AB order pair gives A plus B belongs to R. Is true for all A and B belongs to set of real numbers. It is always true. A and B belongs to R, A plus B belongs to R is always true. Implies the addition, that is plus sign, is a binary operation in R. Addition is a binary operation in R, since it satisfies the definition of binary operation. For all AB belongs to R, A plus B belongs to R is true. So addition is a binary operation. Now we will show it satisfies the definition of associative. Since A plus B bracket plus C is equal to A plus bracket B plus C. For all A, B and C belongs to set of a real number. It is always true. For example, 3 plus 4 plus 1 is the same as 3 plus bracket 4 plus 1. Implies addition is associative in set of a real number. Combining the above two, that is, addition is a binary operation in R, addition is the associative in R. In general, we can say, therefore, addition, that is plus sign, is a associative binary operation in set of real numbers. Addition is a binary operation in R. Addition is associative in R. Therefore, addition is a associative binary operation in R. Clear? It satisfies the binary definition of a binary operation, also satisfies the definition of associative. Therefore, addition is a associative binary operation in R. Case 2. That is multiplication. Solution. Into sign represent the multiplication, so that R cross R to R. AB order pair belongs to R cross R. A into B belongs to R is true for all AB belongs to R. AB order pair belongs to R cross R. A into B belongs to R. When multiplication operates on AB order pair, it gives A into B belongs to R. It satisfies the definition of binary operation. Implies multiplication, that is into sign, is a binary operation in set of real numbers. Into sign, that is multiplication, is a binary operation in R. Since A into B, since bracket into C is equal to A into bracket B into C for all ABC belongs to R. For example, 2 into 3 bracket into 5 is the same as 2 into 3 into 5 bracket. Bracket of 2 into 3 into 5 is the same as 2 into bracket 3 into 5. Implies multiplication is the associative. Multiplication is the associative in set of real numbers. ABC belongs to R. It satisfies bracket A into B into C is equal to A into B into C bracket. It is the definition of a associative. Multiplication satisfies the definition of a associative. If this equal to this, then the product is the associative. ABC belongs to R. A into B bracket into C belongs to R, which is same as A into bracket B into C. So multiplication is the associative in R. Multiplication is a binary operation in R. multiplication is associative in R. In general, we can say, therefore, multiplication is a associative binary operation in set of real numbers. Addition is a associative binary operation in R. Multiplication is a associative binary operation in R. Hence, the statement is proved. Addition and multiplication are associative binary operation. Clear? Clear? Okay. Note down. Note down. Next question. So that subtraction and division are not associative binary operations in set of real numbers and set of real numbers without zero respectively. To show subtraction and division are not binary operations in the set of real numbers and set of real numbers without zero. Prove or solution. Case 1. First subtraction minus, that means sign of subtraction, so that we have to show subtraction is not associative binary operation in set of real number and division is not associative binary operation in R minus set of 0. So subtraction, so that R cross R to R. AB order pair belongs to R cross R. A minus B is true for all AB belongs to R. A and B belongs to R. A minus B belongs to R is true always. Implies subtraction is a binary operation in set of real number. Subtraction is a binary operation in set of real numbers. Since A minus B bracket minus C is not equal to A minus bracket B minus C. For example, 5 minus 3 bracket minus 2 is not equal to 5 minus 3 minus 2. Clear? Since A minus B bracket minus C not equal to A minus bracket B minus C. For example, 5 minus 3, that is equal to 2 minus 2 equal to 0. Here 5 minus 1, that is equal to 4. This not equal to this. Implies subtraction is not associative in set of a real number. Subtraction is a binary operation in R, but subtraction is not associative in R. In general, we can say that is therefore subtraction is not a associative binary operation. Therefore, subtraction is not a associative binary operation in set of a real number. Clear? Subtraction is not associative binary operation in set of a real number. Clear? Okay, next case 2. That is division. Division so that A cross A to A, where A is the same as set of real numbers without 0. A represents set of real numbers without 0. AB order pair belongs to A cross A. A division B, A and B are not 0. Is it true for all AB belongs to R minus, that is A. AB belongs to A and B belongs to A. That means R minus set up 0. AB order pair belongs to A cross A. A division B belongs to A for all A and B belongs to A. That means division operates on the order pair AB gives A division B, which belongs to A. A means R minus set of 0. It is always true. Implies yes. Division is a binary operation. Division is a binary operation in set of real number except 0. Clear? Division is a binary operation. Since A division B bracket division C is not equal to A division bracket B division C. For example, 10 division 5 division 2 not equal to 10 division bracket 5 division 2. This not equal to this. Implies yes. Division is not associative in R minus set of 0. Division is not associative in R minus 0. Division is a binary operation in R minus set of 0. but division is not associative in R minus set of 0. Clear? In general we can say, therefore division is not a associative binary operation associative binary operation in R minus set of 0. Division is not a associative binary operation in R minus set of 0. Similarly, subtraction is not a associative binary operation in R. Subtraction and division are not associative binary operation in R and R minus set of 0 respectively. Clear? Are you clear? Okay, note down. Next, existence of identity element on non-empty set capital A with respect to binary operation star. Existence of identity element in A. At what condition the identity element belongs to A? Definition: let star be a binary operation on non-empty set capital A. Let star be a binary operation on non-empty set capital A. The set capital A is said to have an identity element. Let star be a binary operation on non-empty set capital A. The set A is said to have an identity element if there exists a unique, that means one and only one. If there exists a unique element E belongs to capital A, so that A star E is equal to A. which is the same as E star A. For all A belongs to capital A. Where E is equal where E is equal to identity element on A with respect to the binary operation star, where E is equal to the identity element on A with respect to the binary operation star. Existence of identity element in A. Existence of identity element in A, where A is a non-empty set. What is the definition? Let star be a binary operation on non-empty set capital A. The set A is the set to have an identity element if there exists a unique means one and only one element E belongs to A, so that A star E is equal to E star A, which is equal to A. For all A belongs to A. E is equal to the identity element on A with respect to the binary operation star. A contains, capital A contains the identity element A, which is unique. That means one and only one. If this condition is satisfied, and E is unique, that means one and only one in capital A, satisfying A star E is equal to A, which is same as E star A, for all A belongs to A, where E is equal to the identity element on A. The non-empty set capital A is said to have an identity element, that is E, if this condition is satisfied. The non-empty set capital A contains the identity element which is unique, that means one and only one, if this condition is satisfied. That means A star E is equal to A, which is equal to E star A, for all A belongs to capital A, where E is equal to the identity element in A or on A with respect to the binary operation star. E is equal to the identity element in A. For example, the integer 0 belongs to set of integers. It is clear that 0 belongs to set of integers. The integer 0 belongs to Z is called the identity is called the identity element on Z. 0 is equal the identity element on Z with respect to the binary operation, that is addition. The addition is denoted by plus sign. The integer 0 belongs to Z. Z contains 0. It is clear that 0 belongs to Z set. 0 is called the identity element on Z with respect to the binary operation plus, that is addition. Addition is a binary operation on Z. Since a plus 0 is equal to a is equal to 0 plus a for all a belongs to Z. For any element in Z, a plus 0 is equal to a or 0 plus a is equal to a. Here the binary operation is addition, that is plus sign. Satisfying this condition. Here the binary operation is addition. Since a plus 0 is equal to a, 0 plus a is equal to a, for all a belongs to Z, 0 is equal to the identity element. 0 belongs to Z. The identity element must be belongs to the given set. Here the given set is Z. It is clear that 0 belongs to Z is called the identity element on Z with respect to the binary operation addition. So 0 is equal the identity element on Z. Clear? Since it satisfies a plus 0 is equal to a, which is equal to 0 plus a, for every a belongs to Z. Z means set of integers. A is an integer. For every integer, a plus 0 is equal to a, 0 plus a is equal to a. So 0 is the identity element on Z with respect to the binary operation plus. Next example. The integer 1 belongs to set of integers is called the identity element on Z, that means set of integers, or Q, that means set of rational numbers, or set of real numbers. With respect to the binary operation, the integer 1 belongs to Z. It is clear that 1 belongs to Z. Is called the identity element on Z or set of rational numbers. Z means set of integers. Identity element on set of integers or set of rational numbers or set of real numbers with respect to the binary operation multiplication, which is denoted by the into sign. Since a into 1 is equal to a, is equal to 1 into A. A into 1 is equal to A. 1 into A is equal to A. It is satisfied this definition for all A belongs to set of integers or set of rational numbers or set of real numbers. A may be set of integers or A is any element in set of rational numbers or A is any element in set of real numbers. A into 1 is equal to A, 1 into A is equal to A. So 1 is called the identity element on Z or Q or R. That means set of integers or set of rational numbers or set of real numbers with respect to the binary operation multiplication. Since A into 1 is equal to A is equal to 1 into A for all A belongs to Z or Q or R. 1 is the multiplicative identity on Z or Q or R, and 0 is the additive identity on Z. Clear? Are you clear? Okay, note down. Next, fourth case, existence of inverse of an element on non-empty set capital A with respect to binary operation star. Existence of inverse of an element on a non-empty set capital A. Inverse of an element on non-empty set capital A. At what condition inverse of an element is exist in A? When the binary operation is star. When the binary operation is star. At what condition the binary operation, at what condition the inverse of an element is exist? At what condition the inverse of an element on a non-empty set is exist? What is the definition? With respect to the binary operation star. At what condition the inverse of an element in A, where A is non-empty, is exist with respect to the binary operation star. What is the definition? Let star be a binary operation let the star be a binary operation on non-empty set capital A. Let star be a binary operation on non-empty set capital A. If E is the identity element on A where A is non-empty. If E is the identity element on A with respect to the binary operation star, then an element A belongs to capital A is said to have an inverse element B belongs to A, so that A star B is equal to E is equal to B star A, or A star A inverse is equal to E is equal to A star A inverse star A. A star B is equal to E, which is same as B star A, or A star A inverse is equal to E. E the identity element in A, which is same as A inverse star A, where B is the inverse of A, denoted by A to the -1, read as A inverse. It is the definition of existence of inverse of an element on a non-empty set capital A. Inverse of an element on non-empty set A exists if this condition is satisfied. A star B is equal to E, which is equal to B star A, or A star A inverse is equal to E, which is the same as A inverse star A, where B is the inverse of A denoted by A to the power -1. If this condition is satisfied, then the inverse of an element on non-empty set exists. If this condition is satisfied, where E the identity element on A with respect to the binary operation star, B is called the inverse of A. B is called the inverse of A denoted by A to the power -1, read as A inverse. It is the definition. If this condition is satisfied, A star B is equal to E is equal to B star A, or we can say A star A inverse is equal to E, which is same as A inverse star A. B is the inverse of A, where E is the identity element in A with respect to the binary operation star. A is an element in capital A. A is an element A belongs to A is said to have an inverse element B belongs to A if this condition is satisfied. The inverse of A, small a, in A is exist if this condition is satisfied. For example, the integer m belongs to z. Minus m is the inverse of m. M belongs to z. M is an integer in z set. Minus m is the inverse of m on set of integers. Minus m is the inverse of m on z. With respect to the binary operation that is addition. With respect to the binary operation, minus m is the inverse of m on z. Z is the set of integers with respect to the binary operation plus. As m plus minus m is equal to 0, is equal to minus m plus m. Since the binary operation is plus, since 0 is the identity element, on z, that means set of integers. 0 is the identity element on z with respect to the binary operation, that is addition. 0 is equal to is the additive identity, or 0 is the identity element on z with respect to the binary operation, that is addition, denoted by the plus sign. 0 is the, here a is taken by m, b is minus m. B is the inverse of a, that means minus m is the inverse of m. M plus minus m equal to 0. So minus m is called the inverse of m, which is same as minus m plus m. Since 0 is the identity element, here a star b is equal to e. E is the identity element on a. Here a is taken by z. Clear? Okay. Next example. The integer m belongs to z. The integer m belongs to z and m not equal to 1. Does not, m is any integer, but m not equal to 1. Does not have the inverse on z. with respect to the binary operation multiplication. M is any integer, but M not equal to 1 does not have the inverse on Z. Does not have the inverse on Z with respect to the binary operation, that is multiplication. Since M into B is not equal to 1, which is equal to B into M. Here A is given by M and B the inverse M and N. M B belongs to Z. M into B not equal to 1 and B into M not equal to 1. Since 1 is the identity element on Z, that means set of integers with respect to the binary operation multiplication. M belongs to Z, but M not equal to 1 does not have the inverse on Z with respect to the binary operation multiplication. Since M into B is not equal to 1, since 1 is the identity element on Z with respect to the binary operation multiplication, A star B is equal to E. E is the identity element. Under multiplication on Z, 1 is the identity element. M B belongs to Z. The product is not equal to 1. B is not the inverse of M. That means the inverse does not exist on Z with respect to the binary operation multiplication. Since MB is not equal to 1, which is not equal to B into M. B is not the inverse of M. MB belongs to Z. M not equal to, it is only possible when M is equal to 1. Here it is given by M not equal to 1. Since M into B not equal to 1, B into M not equal to 1, the inverse of M does not exist on Z set, that means set of integers with respect to the binary operation multiplication. Clear? Example. A belongs to set of rational numbers, or A belongs to set of real numbers, and A not equal to 0. A belongs to set of rational numbers and A belongs to set of real numbers, N not equal to 0. 1 by A is the inverse of A on inverse of A on set of rational number or set of real numbers. Since on A with respect to the binary operation with respect to the binary operation multiplication, which is denoted by into sign. A belongs to set of rational numbers, A belongs to set of real numbers, A not equal to 0, that means 1 by A is exist, is the inverse of A. Since A into 1 by A is equal to 1, which is same as 1 by A into A. A into B is equal to identity element. B means 1 by A. Or A to the minus 1 is the inverse of A. 1 by A is the inverse of A. As 1 is the identity element, as 1 is the identity element on set of a rational number or set of a real number with respect to binary operation, that is multiplication. Clear? A belongs to set of rational number or A belongs to set of a real number, A not equal to 0. That means 1 by A is exist, is the inverse of A on set of rational numbers or set of real numbers with respect to the binary operation multiplication. Since A into B, B means 1 by A is equal to 1, 1 is the multiplicative identity on set of a rational number or real number, which is same as 1 by A into A. As 1 is the identity element, that means multiplicative identity on Q or R with respect to binary operation multiplication. Are you clear? Okay, note down.